Okay, welcome everyone. Thanks for coming early Monday morning to the second week of topology, or 8th week of the lecture, whatever you want to call it. Today I would like to, well, we wrap up graphs a little bit. We will see graphs. They are around everywhere. We will see them all the time. But I will wrap up with some last nice, well, fact theorem about graphs, which is really not obvious. It's still pretty cute. And then I will go to a higher dimensional picture, so graphs at one-dimensional objects, and I will go to two-dimensional objects, which is kind of the next step we would like to study in topology. But let's start with graphs. Okay, so graphs are really cool, and you can ask various questions about graphs. And here's a question I could ask. The notion is due to Euler, that's where the name comes from. Eulerian cycle or circuit is just, I'll see an example in a second, is something that visits every edge exactly once. So you go around your graph and you visit every edge exactly once. And similarly, or in this spirit, we call a graph Eulerian if it emits an Eulerian cycle. And it's not absolutely obvious whether there should be any examples or what kind of graphs satisfies this property or anything. And I will show you a really nice solution to the problem. But first, let's have a look at an example. Life is boring without examples. So here we go. So if I have my little graph here, so this is always the same. I think these are 12 pictures of the same graph. And I made 12 pictures in order for you to see the path and that it visits, well, the path I've chosen here, and that it visits every edge exactly once. So we start here at this vertex, and we want to go back to that vertex by moving around and visiting every edge exactly once. And here's, for example, a solution to that problem. So we move first a little bit along the triangle, and then we go around this triangle, and eventually we will end up with a complete round tour that visits every edge exactly once. Right? So the main point here is that I would like to visit every edge exactly once. I don't want to visit an edge twice. I don't want missed edges. I just want to visit everything. I don't care about the vertices. So I can visit a vertex several times. I don't care. But I want to visit every edge exactly once. A little bit silly, the little warning that you essentially can ignore. So if I have, well, here's another graph. It's still this beast here, and it still has the same path because obviously the other vertices don't have any edges. So I need to visit every edge exactly once. So you can always throw in a lot of vertices without edges and they don't change anything. Just keep that in mind. It's not super important. We usually focus on the interesting part, and the interesting part is my graph G here, which this one is Eulerian. Okay? So can we find a graph that is not Eulerian? Well, I can. So here's a very simple graph. There's just two vertices and one edge. And I would like to go around visiting every edge exactly once, and this just can't work. So if I start here, I need to go here, and I can't return anymore because I already took the edge. So there are graphs that are Eulerian, and there are graphs that are not Eulerian. And a priori, at least I don't know how you feel, it seems to be quite hard to decide whether a graph is Eulerian or not. I mean, this is pretty fancy. It takes you a while to find this path. For this one, it's easy to see, but if you have a really huge graph, I certainly can't tell just by looking at it, where that's how it feels like. And there's a really beautiful solution to that problem, which is due to, well, who could it be? To Euler. I show you the solution. And Euler's argument, actually, which is pretty amazing. But let me actually now take a slight detour, not really a detour, but a slight detour, to motivate where the problem actually comes from. And it came from a real-world problem, if you want, and graph theory is really one of the most applicable fields in mathematics altogether. It's extremely amazing. It's not just beautiful. Well, obviously, I like it, but beautiful is a little bit, well, depends on the person, I guess, but it's very, very applicable. And it actually came from a little puzzle people quite a while ago asked in Königsberg. So this is a map of Königsberg. It's not, the city is no longer called Königsberg, if you would like to Google it. It's called Kaliningrad. It's somewhere in Russia. But this is an old map. And people were asking, you can see those 7 red bridges that are marked here. and people were asking the question, like a little puzzle, can we have a Sunday afternoon walk, just walking around, passing every bridge exactly once, right? So you just start somewhere here, and you want to pass every bridge exactly once, so you do something like, oh, this doesn't quite work, so you do something like this, and you get stuck. So people were wondering for quite a while whether this is possible, and then Euler came around, and Euler is, of course, was of course very brilliant. And what Euler did is the birth of graph theory, and this is really how I would like you to think about graphs. We took a real-world problem, or a real-world puzzle if you want, it's not really a problem, but anyway, a real-world problem, and you abstract it into something that's much easier. So Euler just says, okay, and that's a true story, so Euler just said, without knowing what a graph is, what we do here is we put all of these into vertices, and every bridge will become an edge. Well, whatever kind of graph you get is the one here. So you see the 7 bridges are now 7 edges, and for example, the little island in the middle is this vertex here. And this is a pretty cool idea. Why is that a pretty cool idea? Because now Euler just said, well, I am pretty lazy. I don't need to walk around Königsberg to check whether this is possible or not. I can just stare at my little graph here, and I can just play around with my little graph. And Euler realized the following. Okay, so let's say we want to start here, and we want to end here. It doesn't really matter where, it's a very symmetric graph. Well, eventually, we need to enter, what is a good color here, maybe this one. We need to enter somewhere this vertex, but we want to go back to the purple one, so we need to leave the vertex as well. There you go, you need to leave the vertex as well, and you do go around further, but as you can see, there's still a missing edge here on my bottom vertex, so eventually I need to take this edge, and then I'm stuck. I can't go back anymore. It's a little bit more fancy than my little example from here, but eventually you get stuck in this process. Okay, and that's really brilliant. So without ever walking around Königsberg, just Euler solved that problem and created the field of graph theory at the same time. Right? So that's just, and that's how I would like to think about a graph, where it's really some real-world problem that you model, and then it's much easier, so you just need to look at abstract properties instead of whatever, walking around in Königsberg. And graphs are nowadays really everywhere. So the brain, for example, is a graph. You can think of neurons, and the neurons are connected, and a lot of properties of the brain, so modern neuroscience, studies graph theoretical properties of the brain. It's a very, very exciting field. So mathematics here was way ahead of, well, the real-world sciences in this case, but it's a really cool story that you just have some abstract object mimicking something in the real world, and abstract properties that you study just for the sake of it, in the end determine something in the real world, which is actually pretty cool. Okay, so Euler went a bit further, right? So now we have an abstract picture. We can actually forget about Königsberg, and we can think about graphs. And that's when Euler asked the question about the Eulerian cycles. And we came up with the following absolutely crazy theorem that tells you exactly, very simple, whether a graph is Eulerian, so it admits an Eulerian cycle or not. And it's if and only if every vertex has even degree. And we'll see in the proof in a second why you want that. If and only if. It's an absolutely great criterion, right? Think about back for something like 5 minutes. At least to me, it looked like almost impossible to check whether a graph is Eulerian or not. I could show you the picture of the path again. So the path is pretty complicated, but I can just stare at my graph, and every vertex has degree 4 in this case, so I know for sure, without really finding the path, that there will be a Eulerian cycle, just by Euler's abstract argument, by thinking abstractly about a problem, which is really amazing, and the whole point. Very simple criteria, and it's if and only if. Every vertex has even degree. Fits to my degree 0 vertices that I just put in randomly in the first picture. They, of course, don't change anything. So let's have a look at the proof, Euler's original proof. It's pretty amazing and very simple, and again, kind of a really good example of how abstract thinking gets you quite far. Okay. So the first part of the proof is exactly what I said before. So assume that there is some, I don't read the text, we look at the example. Assume that there is some vertex of odd degree. In my example here, it will be a vertex B. Well, vertex B clearly has odd degree, and I'm trying to find a cycle somewhere. And eventually, no matter what I do, I go here, H1, then H2, then H3, then H4, and I need to take all edges, so H5. So I started here, and now I'm stuck at B because I can't go back anymore. And that's a very simple idea. So whenever you're at a vertex, the going in and going out operation, using different edges, always is kind of an even operation on the number of edges. So as soon as you have an odd number of edges, you will always end up being stuck in the end at the vertex. Right? Does that make sense? So as soon as you have an odd degree, you will get stuck at that vertex. Now you could say, okay, then I start here, but then you get, for example, stuck here, and to kind of always turn around. What you really need is every vertex has even degree. And here for A, for example, you can see it. A is perfect. We just go into A and exit A, and A is never really a problem. Same for D, but B and C here are the little troublemakers. They have odd degree. And this is really simple, right? It's just a really simple idea. You get stuck because, well, exactly this holds if you go into a vertex and you go out, that's an even operation on the number of edges, right? So as soon as you have something, have an even number to start with, you always subtract 2 by every visit to the vertex, and you end up at 0, so you're good. If you have odd, you always subtract 2, but you don't end up with 0, so you get stuck eventually, and you can't leave the vertex anymore. So that was Euler's idea, just from exactly from this problem, where you can observe it pretty simple, easily. Just, okay, here, and I get in, I get out, I get in, and then I get stuck again. So in, out, in. And no matter how I do it, doesn't matter, I will always get stuck at that vertex. Pretty amazing argument. So this is one direction. This is this direction. So this was this direction. If it's Eulerian, then we know that there must be an even number of, every vertex needs to have even degree. So let's have a look at the converse. The converse is a bit trickier, but we still can do it. So essentially what you need to do, let me get rid of the text, let me go to an example, and then go back to the text. Essentially what we want to do is we want to construct one of those inductively by looking at smaller graphs. So what I will do, and I explain that in the text in a second, I will have a smaller graph, that's a graph in, what is it, red here, and I have many little other graphs. I have a green graph down here, what is this one, a purple graph here, a little bit of a boring yellow graph here, yellow is not really visible, but anyway, and a blue graph up here, and all of them have nice Eulerian cycles, and I piece everything together into a bigger cycle. So let's have a look at the argument. So keep that in mind. We'll come back to the slide in a second. Keep that in mind. That's what we want to do. Okay. So if every vertex has even degree, we know that G can't be a tree because trees have leaves, and leaves have odd degree, well, by definition. Cool. So we have some cycle in the graph. That was the construction of a tree. There's something, C. That's this guy. Oops, that's the red one in the picture here. If it's already what we were looking for, well, fine, we are very lucky, we are done. But in general, it won't be. So what do? We just remove everything else from the graph and end up with the red one here. And whatever remains is a potentially disconnected graph. So this is G prime. If you remove red from G, you get G prime. Very good. Okay? I just remove inductively. It's a smaller graph. It has fewer edges, obviously. That's the whole point. I removed edges. So we should be able to argue by induction. Observe that I removed something of even degree because it was a cycle. So whatever remains is still of even degree. Well, let's see that in the example here. So here, the vertex, what is a good color? Maybe this one. The vertex has 4 edges, and I removed 2 of them, namely the part of the cycle, so the vertex remains with 2 adjacent edges. So this operation keeps the property of the even degree. So this graph is again a graph with even degree. It has fewer edges, so you could use induction on the graph, and induction gives you those funny cycles. Right? So induction gives us whatever, some finite number, C1 up to Cn, And we piece them together now as follows. So we have our little, let me try to get rid of everything here. I need a little bit, I need to start over again. We have our little cycle in the middle, the red one. I should do it in red, the red one. And we walk around, so it is a Eulerian cycle, so we can walk around. And whenever we hit a vertex that is in G prime, we take a detour over the other graph. Okay, so we start here. This vertex, so here at S. This vertex lies in G prime, so we take a detour over, and it doesn't matter in which direction, it's a cycle. We take a detour over G and have our little detour here. Now we move to yellow, we take a detour over C for yellow. C for yellow is a bit boring, so nothing happens. We move along, we take a detour over purple. Here again, take a detour over purple. We move along, we take a detour over green, take a detour over green. We move further, and we have our Eulerian cycle. That makes some sense. So all I'm doing is I have an inductive argument, and I find some cycle by knowing that my graph is not a tree, remove it, I get a graph with the same property, and piece everything together into an Eulerian path. This direction, I admit, is a bit trickier than the other one, and it took Euler way longer to come up with this idea. So don't feel too lost. So it also took Euler quite a while, and Euler certainly was very brilliant. But this one is a really cute argument. I would be happy if you try to remember it. So we really just get stuck if you have an odd degree vertex. It's very simple. Okay. So this is a really good theorem. Let's go back to the theorem. It's an if and only if criterion for this graph to be Eulerian. And again, I said again, if you just stare at the definition, it's absolutely not clear that there should be some nice theorem like this at all. It's absolutely not clear at all. Just constructing those is a bit tricky in general. Okay. And Euler just went on. Euler is Euler, I guess. And also asked the question about, we'll see a picture in a second. Maybe we don't want cycles, but maybe we want the same property, just starting somewhere, moving around, taking every edge exactly once, something like this. So let's say these are all my edges here, and this would be the path. And is there any reasonable property for those as well? We call this guy a Eulerian path to distinguish it from a circuit. So it's not closed. It has a distinct start and end. Well, it's kind of the same question. And well, we'll look at an example in a second. And this works if and only if there are two vertices of odd degree, which is start and end. Remember that I told you you will eventually get stuck when you have odd degree. But for start and end, that's not a problem. You want to start anywhere and you want to end anywhere. So you want to end anyway. So if you are stuck, then that's fine. And that's exactly the property that picks out those graphs. Let me show you an example before I go through the proof. So here's the example of Königsberg. So Euler applied this example also to Königsberg. Again, the graph, we look at it and we count degrees. So this is 3, this is 3, this is 3, this is 5, I guess. So that certainly doesn't work. We want only 2 vertices of odd degree. And indeed, you can't do it. So here's an example that you can't do it. But what you can do, for example, that was a proposed solution here. You could destroy bridge E. So if you destroy bridge E, the vertex goes away. This has now degree 2. This doesn't change. And this has degree 4. So this could be the start, and this could be the end vertex. And indeed, here you have a little path that passes all bridges exactly once. It's a little bit of a drastic solution, I guess, but in principle that could work. So the only point here is that the odd degree vertices, you're allowed to have 2 of them, and they are start and end point of your path that visits every edge exactly once. Okay, we keep this example in mind, and now jump to the proof of the corollary. Or you could also call it the theorem if you want. Okay, and the first thing I observe here is exactly what I said. So we need precisely 2 of them. And what you can do now is you can do the following trick. So you take your graph, you add an extra edge between the two vertices of, what is it, odd degree. So B has degree 3, C has degree 3. We add an edge, the purple one. So this has now degree 4, this is now degree 4. And of course, nothing changes. It's a local operation for the other vertices. So this has still 2, and this has still 2. So what you can do now is you can use the previous theorem, that's why I called it a corollary, to find a Eulerian path in this new graph with the additional edge. And then just get rid of the edge. It's the last one you take, step number 6. You get rid of it, and in this case, C is the start and B is the end. So let's see how that works. So it's 1, 2, 3, 4, 5, and my closed one would be 6. It starts at C, and I know the existence of a closed one by the previous theorem, but I can get rid of the edge again, and I get a path that starts here and ends here. So it's really just an application, a little bit of a smart application of the previous theorem. You just add an edge between the two vertices in question. Okay, let me go back to Königsberg. Okay, to wrap up this part, so a property you could ask about graphs, and it turns out to be really useful in practice, is this property of walking around and visiting every edge exactly once. And you actually have a really, really great, kind of very easy criterion that you can check easily on any graph. You just count degrees, and it gives you a solution, an if and only if solution, to either of the problems. So either you count only even degrees in Euler's original problem, or you count, well, you need two vertices of odd degree for the start and the end. And this was really kind of, I would like to keep this in mind, the start of this field of graph theory, where you now have a lot of those properties that eventually will do something interesting in some real-world setting, whether it is a riddle or a question people ask in Königsberg and we're not able to solve because just walking along doesn't get you really anywhere in the end, and you need to sit down and do some more of the abstract argument here. A very cute argument. It's really, really good. And we will see many more properties along this line, but at one point I'm supposed to make the step to the two-dimensional world, and that's what I'm going to do now. So we say bye-bye to graphs for a second, or maybe not for a second, but maybe for something like a week or so, and we will eventually come back to them, but because they're just way too cool to ignore them. Okay. Something completely different. If you didn't like graphs up to this point, here's another starting point. It's not really completely different, but it looks very different. We'll see. It's still very nice, so don't worry. I have lots of pictures for you. So the main property I was kind of not telling you, the main definition I was not telling you last week, kind of sweeping it under the rug a little bit, is the notion of a homeomorphism, which I want to have on the slide. We'll see several examples, and then we kind of forget about it and use our intuition. But here's the definition. A homeomorphism between two subspaces of some Euclidean space, R to the m and R to the n, is a continuous map with a continuous inverse. Right? So you have f in one direction, it's continuous. You have g in the other direction, it's continuous, and they invert one another. See several examples in a second. And this is the underlying equivalence notion for topology. And I said we kind of change gears a little bit. We go a little bit away from graphs, but actually this is really the higher dimensional analog of isomorphisms for graphs. I leave it to you to think about that for a second, or maybe as we go along in studying homeomorphisms, but this is kind of meant for higher dimensional objects. Just look at it. X could be up to dimension m, y could be up to dimension n, and the graph was just kind of the one-dimensional picture here. So we are not really doing something different, but we're taking a higher dimensional perspective. And what comes out will be, again, very, very useful and extremely great, beautiful in itself, intrinsically, but also very useful in practice. Let me just mention this. Because they're inverses, they're also bijections. So there's a bijection from x to y that's continuous, and there's a bijection from y to x that's continuous, and they invert one another. And then we say that this is a homeomorphism. Slightly strange name, but that's what it is. Sometimes mathematics has slightly strange names. And we call the spaces homeomorphic, just of the same shape. So it's kind of Greek, and it's kind of trying to say they are of the same shape. And I'll give you several examples in a second, so stay with me until I'm done with this slide. So let me just add here 3 observations. So clearly, X is homeomorphic to itself. Take the identity. It's a very good continuous map. If X is homeomorphic to Y, Y is homeomorphic to X. You can swap the roles of F and G. And the transitivity property is also not very hard to show. In other words, this is an equivalence relation, and exactly the equivalence relation we like to throw on to our spaces, and it partitions our spaces. So here's a set of our spaces, and it will partition them in homeomorphism classes, and we'll see several examples as we go along. So this is the equivalence relation that determines topology. It looks very strange, but as soon as you see examples, I promise you it's actually not so bad. Okay, life is boring without examples, so let's do some examples. And I just formulate them in a slightly strange way. I just formulate them in propositions, but essentially they're examples. So the first example says if you have an interval a to b, here's my interval a to b, and I have some other interval c to d, whatever, c to d, then actually they are homeomorphic. So from the viewpoint of topology, they're just the same. In other words, I really don't care about different lengths, right? A, B could be bigger than CD or something. I don't care. They're all the same. And I show you how to do that. And that's why I call it a proposition, I guess. I show you the maps, the homeomorphisms that realizes those. But the takeaway message here is that our equivalence relation here, homeomorphism, doesn't care about lengths. Very different from geometry. I don't care about lengths. All intervals are the same. All intervals are the same. Doesn't matter. And here are the 2 maps. Don't stare at them too much. It's just basically rearranging the start and end points. And this is just a polynomial in the variable, so that's clearly a continuous map. It's actually a linear map. So F and G, just relabeling the endpoints of the vertices. Again, don't stare too much on those examples, but that's roughly how those homomorphisms look like. There's some polynomial type of functions. Not necessarily, they can be a little bit more fancy, but some smooth type nice functions between spaces. The point is, all intervals, this is not the pen, all intervals are the same, so length doesn't matter in topology. I don't care about lengths, whether it's length 1, whether it's length 1 million, whether it's length 0.001, they're all the same. But, and that's kind of the point, they're really lines, right? I really look at the intrinsic property of being a line here. And you can do the same. I call it an exercise. I shouldn't call it an exercise. But anyway, if you would like to do it, you can use similar maps to show that the open intervals are also the same. So here was an endpoint involved, doesn't really matter. And the half open ones are also the same. And we even have this property, maybe I can draw that so if it's open at one side, it's open at the right now, and it's closed at the other side, you can always turn it around. So we also don't care how they live in space. It's really only about the intrinsic properties. Those 2 spaces are the same. They are lines with one honest endpoint, if you want. So they're really kind of the same. And, well, I call it an exercise. You can use those types of maps to do that. That's kind of a nice start. I think that's a pretty nice start. So we want to get rid of this idea of length. It doesn't matter for topologists. I don't want to get rid of it. I would like to focus on intrinsic properties of spaces that if you think it back to what we did last week for graphs or earlier for graphs, I never cared how graphs are embedded or anything. So really I would like to study intrinsic properties like this is a line. So all lines should be the same under whatever kind of notion I come up with. And that's how people came up with this definition. So it's not like people throw in this definition and then study what comes out. You have an idea what you would like to do, and you adjust the definition according to the idea. And that's why I kind of want you to a little bit forget about the formal definition and kind of go with the flow of the idea that we want to study intrinsic spaces intrinsically. I'll show you more examples in a second. Okay, this one is a fun one. So I really don't care about length. So a finite interval is actually the same as a whole line. Certainly very infinite. So one of them is R, one of them is the whole picture, which I even can't draw because it's infinite. And the other one is any tiny part of it, and they are still the same because they're both just lines. And how to think about this? Well, note that this is the open one. So in the open one, if you slow down a little bit, you can actually go arbitrarily far without ever hitting the boundary. If you just slow down. And this is just a bigger picture of the same instance. So they should be the same objects. And they are. And I show you the map doing this. Okay. I claim that it's enough by the previous nonsense to do it for this funny interval. You'll see in a second why it's pi over 2, because I'm using a very well-known function to do it, which just likes pi over 2. And it's this function. So G is this function that's the inverse of the tangent, and this is the tangent function. And as you can see, the only thing the tangent does is it takes, well, this is the inverse, it takes a real line and just stretches it and puts it exactly nicely in the interval. And this is certainly a bijection and continuous, and they're inverses by definition, I guess. And here's the opposite. It takes it and puts it nicely into the interval. And every point has a unique image here. And that's what I mean by you slow down. You either walk very fast in the real line, and you never get anywhere. So you can go, well, you can go as far as you want, or you do it very, very slowly, and you kind of converge to the boundary of the interval, but it can still go arbitrarily far. So this will never hit the dotted line. So dotted line, by the way, is this pi over 2, and this is minus pi over 2. Maybe I should add them here just for completeness. So this one is pi over 2. This one is minus pi over 2. And same here, the picture is just, right, so the inverse of a function is just you reflect the picture along the line here, roughly here, the x equals y line. That's probably horrible, x equals y line. Okay, and this makes sense, at least to me, because as I said, they're kind of the same objects. They're lines, and they can go arbitrarily far without ever hitting a boundary point. I just need to kind of slow down here a little bit in this sense. Kind of fun. So I really completely got rid of the notion of length. You can do that in higher dimensions if you want, using similar maps. So there's no volume, there's no area, nothing. Very different from geometry. We don't care volume and area. You can always rescale everything to make this work. Very similar to photographs. Photographs, I never cared how they're embedded into space. I only cared about the intrinsic properties. We do the same here. Here's another one that I promised last week, and I now show you a proof, actually, that you can even get rid of kind of, well, corners. They're still the same object. One of them just has corners, but we don't care about angles. This is what this proposition is showing, the example. And I show you the proof. It's a bit easier to just show this one because the functions come out nicer. But again, the rotation itself is a homeomorphism. It's continuous, and there's an obvious inverse of a rotation. So I just rotate one picture. I could also rotate the circle. If I rotate the circle, not much changes. And here's the map. It's actually pretty simple. So the square is, well, this one, the whatever, S1, the space is called S1. S1 is this space. So the only thing you do is you rescale your coordinates. So from the square to S1, you rescale your coordinates. So these coordinates by construction satisfy this equation. And that's a very nice continuous map. The inverse rescales the coordinates, and by construction, the rescaled coordinates will satisfy this equation. So I only take the equation and divide by it. And because of the stupid squares, I need the square root here. But all I'm doing is I rescale my coordinates. So here they are of unit length, and here they are of this length given by the absolute values of the coordinates. It's kind of what defines a square anyway. You just rescale the coordinates. So from the viewpoint of topology, a sphere is the same as a rectangle. I just said a rectangle, I only showed it for the square, but now we can rescale the rectangle by using the interval trick along the axis, and you actually get also that a circle is the same as a rectangle. And that's pretty cool. And the maps are relatively harmless, but ignore them for the most part. They're just well-known functions in from analysis. Well, really not hard functions here. Polynomial type functions. So up to rotation. Rotation, I said again, rotation is clearly a continuous map that has a continuous inverse. If you rotate by 60 degrees, that was probably not 60 degrees, but if you rotate by 60 degrees, you can anti-rotate by 60 degrees. So it also doesn't matter how it's rotated in space. I don't know what angles are in topology. I don't know what length is. I only care about the intrinsic properties of those spaces. And here's another one. So S1 is actually almost a real line. And the way to think about this is the following. There's a very nice continuous map, and it's called the Stereographic Projection. I have some more nice pictures in a second for you. You will understand where the name comes from. It's really this idea that you mark the north pole of your sphere, just call it infinity. Yeah? We'll see in a second why you call it infinity. And you define a map down to the real line. So this is S1. This is the real line here. By just, well, what's the image of the point X? Just draw a line between them wherever it ends. That's the image of, well, this was a really bad line. The original one was better. Let me try again. So wherever it ends, there would be the image of the point. So the image of Y roughly is here. Again, my lines are not really good. And the further you go to here, for example, the image of this point will be very far outside of the picture, and that's why I call this point infinity, because its own image, which doesn't exist, I only take it from here, would be given by this parallel line, so it would be somewhere at infinity. And this is really the point of infinity. And the only thing I do here, if you think about it, is I take the real line, which is just a line, and I kind of try to wrap it at infinity and wrap it up into a circle. So the circle, topologically speaking, is just a real line with one extra point, where I take the two infinite points of the real line and I glue them together. But just imagine that I can take my line and put it all together here. And it's given by, you can check that, and here's the map, and the inverse of the map is just reading everything backwards. And where does this name come from? This actually works in any dimension. So looks always the same, but I went one dimension up here, actually. And what you can think of is now I have the plane, and I grab the plane at infinity, which is a bit hard, but anyway, and I wrap it up into a ball. And so if you, the opposite operation is a bit easier. If you have a ball in your hand, and you poke a hole into it, that's the North Pole, and you can actually bend it open, and you get a plane. And the map that realizes that is called the Stereographic Projection, and it's exactly the same idea. So you have some light source somewhere. Right? So this idea here, you can also think about it like having a light source at infinity, and kind of the shadow of a point is the image of the point. In 2 dimensions, in this 3-dimensional picture, it looks a little bit nicer. I have a light bulb at infinity, and whatever it projects down to will end up somewhere here, and you get this nice, well, map from the sphere to the plane. The only point that is not touched is the infinite point, which is exactly the point where I wrap up, or that I removed, where I wrap up my sphere. I hope that picture makes some sense. Note here that this map is completely angle or area destroying. So if you look at the hexagons here, they are much smaller around here than they are around here, but they end up at the same size under the well, light bulb projection to the plane. I hope it makes some sense. So let's have a look, and you all have seen this before, actually, because that's what people do. Well, I guess our Earth is again when mathematics predated some real world applications. Our Earth is clearly, well, maybe not clearly, but I guess we all believe that it is a sphere. But if you open a book with a map of the Earth, well, it's a book, so it will be something plain. And the way to do this is to use the stereographic projection. So it's upside down compared to the other picture. Now I've marked the South Pole. In this stolen picture, the South Pole is marked, but it's the same idea. You project everything up to the plane, and you can see that everything is kind of distorted. So Australia here is much bigger than North America, for example, because Australia is more like here, and North America is more like here, maybe, something like that. But in the end, you get a picture, a nice picture here. So Australia, that's a bad color. So Australia is here, it's much bigger than something like North America. And North America would be here, so it gets a smaller image. And Australia is maybe here, so it gets a bigger image. Oh, that was a bad picture. But anyway, so it gets a bigger image down here, something like that, maybe. So if you really read maps carefully, you note that actually they are distorted because you always end up with some distortion here in this operation. So here again, topology predates some real-world applications, production of maps, and it comes from this idea of having this map from the sphere to the plane, or the easier one, the one-dimensional one, from the circle to the line. You can do different things. I just mentioned that here. So people thought about this for a long time. So we will work with this one because it's mathematically the nicest, but you can do different things. You can imagine your light bulb sitting in the middle of the sphere, and then you project half of it, but maybe you get slightly better pictures. So people played around with this idea quite a lot, and there are various different projections. We only focus on this one, the stereographic projection, because it kind of fits most nicely. You could also phrase those in terms of topology, but I just added them for completeness. So if you Google some of the others, they all look the same. They do slightly different jobs by keeping certain angles a little bit nicer, but eventually you need to destroy area and angles, and everything is a little bit stretched here. But in topology, we actually don't care anyway, so that's kind of fine. Okay, I would like to end by defining the main players of the next 1.5 weeks, surfaces. So we have already seen several surfaces, and we would like to study them up to this notion of homeomorphism, which is a bit strange. So we need some really good tools to do that. So I admit, of course, I know this now for a long time, but if you first see this idea that the sphere is not very different from a plane, it's a bit different. There's one extra point, is where the light bulb sits, but it's not very different. It's a little bit shocking in some sense, and topology is really an amazing step in the history of science, from really abstracting and getting really cool intrinsic results about spaces, which in the end, here's an example again, turned out to be extremely useful in practice. This is a really cool example, very similar to the Euler graph type example, just with those type of objects. Okay, let me introduce the main players, and then you're good to go. Okay, a surface, I will show you pictures in a second, but a surface is something that is locally flat. It's locally a disk. Well, I say it's either a coordinate plane, so locally means there's for every point you have a neighborhood that is a coordinate plane, or for every point you have a neighborhood that is a disk, and I already showed you that this is actually the same anyway. So you can think of either having disks or coordinate planes at every point, but that's what I call a surface. And the two-dimensional one comes into the game because it's a plane. So this is part of R2, and this is a disk. So this is what people call D2. So disk, by the way, is filled, and this one is filled as well. So every local point has a neighborhood of this form, and it's kind of the next. Well, let's compare this with graphs. It's kind of the next step for graphs. If you think about a graph, so here's a graph, then every local point has a neighborhood, which is actually a smaller dimensional disk. Well, a smaller dimensional disk is just an interval. So every point has a neighborhood that's an interval. Let's ignore the boundary points for a second. Every point is an interval, and here every point has a local neighborhood, which is one dimension higher, which is a disk. So these are kind of the two-dimensional analogs of graphs, if you want. And they really play the role of two-dimensional graphs. It's kind of very amazing. Okay, so let me give you examples. A plane is an example because the plane is locally a plane. Or I could draw the disk for you. I will draw the disk for you. Here's a disk, local disk in the plane. The point is always the point. So locally here means for every point. So I fix a point and I show you a disk. And this works, of course, for every point. And it actually doesn't really matter how it looks like. Here's like another one. Here's another one. Here's another one. So they're all surfaces. So a plane is a surface. That's a good news, I guess. Because obviously a plane is a two-dimensional object. And this should be a generalization of the notion of a disk or a plane. You can have way more complicated looking things. So here, a non-standard one. Still, I can easily draw my little disk here. Could be curved. I can easily draw my little disk here. So again, this notion gives us the freedom of kind of bending things in space because we only care about kind of local intrinsic properties. And it doesn't really matter how the disk lies. We already know that we can bend them anyway, as long as it is a disk. You good? It's a curved surface in R3. A disk is a surface. I can show you the disk in the disk if you want. So every point has a local neighborhood that is a disk. This one is a bit trickier, but every point still has a local neighborhood that is a disk. So this is a disk with a hole in the middle, and it's called an annulus. I will use the notation A for this beast. And if you think of the annulus in the following way, so I think of my annulus as being here. So this part is filled, and now I take my hands and pull the outside up. The little circle stays downstairs, and I pull the outside up. What I actually get is a cylinder. So whatever, this is the inside hole, for example, and this is the outside hole, and I just pulled it up. And topologically, the pulling up operation, I haven't written it down in coordinates, but you can. So topologically, these are actually, again, equivalent. And here you can see the local disks wherever you want to see them. That's not a plane anymore, right? That's already a more complicated object, but it's part of the definition of the surface, and it's the two-dimensional object, as you can see. We'll do the boundary in a second. A sphere. Yeah, a sphere. Let's draw a little disk here. There you go. A little disk on the sphere. So a sphere is clearly not a disk, but it is a surface, because locally it is actually a disk. Think of a tangent space along the sphere. The tangent space, if you project it a little bit down to the sphere, you get your little disk. This object here, well, a bit more complicated. I show you real-world examples of these objects in a second. But here I have my little disks. Every point has a disk. Even if I draw it like here, I can make my disk as small as I want to. Everything kind of works. Let me show you real-world examples of those. It's a bit easier to imagine. So the sphere is actually just a soccer ball. It's hollow. I need to say that again. It's hollow. Soccer ball is hollow. And a soccer ball, if you want, has those little disks. And you can actually see them here. For example, this hexagon is a disk. Right? I showed you that you can, the square is equivalent to the circle. Not much different. You can show that any polygon is equivalent to a circle, or to a disk in this case, because it's filled. So this is actually the hexagon here on the, sorry, it's not a hexagon, I guess. The pentagon here on your soccer ball is actually the local disk. And so are the hexagons, and so would be, well, a real local disk somewhere that I could draw here. Hope that makes sense, right? So this is, again, a surface. So a soccer ball is a surface. Whatever you say about surfaces, it will hold for soccer balls. That's pretty amazing. Subsets. The torus, the object from before, I said again, it's hollow. So people often call it a donut, but it's really more like a swim ring. It's hollow. And it has the local disks just everywhere. So here's a local disk. Whatever, here's a local disk. And everything we can say, there's a swim ring, is a surface, and it's not a soccer ball, as you can see. It's kind of a different type of object. We don't know that by now, but it will turn out to be a different type of object. This notion has quite a bit of freedom. So a lot of real-world objects, essentially everything that is two-dimensional and happens in the real world is a surface. So if you're wearing a pair of pants, like I'm doing right now, and there's a patch on your pair of pants, I'm sorry I don't have any patches, but the patch actually is a local disk. So this is a surface. Ignore the word boundary, we'll do the word boundary next time. So the little patch on your pair of pens, that's actually a disk. So the pair of pens is again an example of a surface. And you can come up with many, many more examples. Like everything in two-dimensional that lives in the real world should be a surface in some sense. So it's a really, really big notion. We need to leave in a second, so ignore the projective plane. It's a very complicated surface. This is about the most complicated surface we will see. So let's ignore it for now, because people are already waiting outside. Let me just show you another one. A Möbius strip. So all I'm doing here is I take a piece of paper and I wrap it around by identifying those two edges in an opposite way. I take my piece of paper, it's just a string, and I wrap this piece around. If I do that, I get a cylinder. But if I do that with a twist, I get this funny object here. So I twist it and I draw it together. I should have been better prepared, and I should show you. So you can build this at home. I should show you how that works. But it's a Möbius strip. And the last one for today is, again, a very complicated object. But locally, it's a disk everywhere. And people build this. So it's a disk. It looks a little bit strange. It's a self-intersecting thing. And a very complicated object. It's called a Klein bottle or Klein surface. So the story is that it was Klein came up with it. Okay, fine, fair enough. And it was mistranslated from German into English and then mistranslated back from English into German, and then ended up to being a bottle. But actually, it's a surface. It's just called the Klein surface. And what we will do next time is we will study them in more details. So let me just wrap up by showing you non-surfaces. So whenever you have something that is locally not a disk, it's not a surface. So you can imagine my book with 3 pages. If you remember my book with 3 pages, the binding of the book, every vertex has a neighborhood which is not a disk. It's more like a binding, like a little part of a book. So this is not a surface. So not everything is a surface, but quite a few objects are.